Thank you, Steve. Thank you so much. So I didn't put a title here. I very much appreciate things like this. Okay, today is probably the busiest day of the year in Northwestern with homecoming. I arrived yesterday from San Francisco. I leaving tomorrow morning, but if I were not able to do things like this, or occasionally to write a paper, sometimes being the lead author or something, I wouldn't be able to do this job. And the beauty of Northwestern is that allows for someone to be able to do this. So, and also to be surrounded by people who are interested in these kinds of things. So I was talking with Steve Davis about this. I have been asked to review 2 books about Poincaré. They are apparently the first that have appeared in English. One is Springer, the one is Princeton University Press. Because I was writing a review, and I got the review actually today in Physics Today. Of course, people are much better coming up with titles than sometimes one is able to. And the title that they put could have been the title of the talk, is 2 Takes on a Masters of Mathematics, Physics, those you know, and the Written World. Written Word. So that's what I'll try to say a few things about Poincaré. But I'll first kind of try to spend a few slides trying to place him in the context of his times. Okay? He followed people like this, and I'll have more to say about this, that they were of the view that if you inserted figures in a mathematical argument, you weaken the argument. So Lagrange, many of you probably know this, he prided himself in saying this book contains no pictures. Okay? And Laplace was of the same persuasion. Everything was extremely rigorous, no pictures, very rigorous. And Poincaré, this is the front page of his collected works, and these things used to be here in the Physical Sciences Library. Now it's in the Math Library. If you take a picture, this is what Poincaré wrote. Okay? No co-authors anywhere. Okay? Not a single one. But the other thing is that there were no pictures in any of these. I mean, you can flip the pages, and occasionally you see a little sketch, but no pictures whatsoever anywhere. Now, Poincaré's productivity was enormous, but doesn't sort of match Euler, because this is what he wrote. Again, by himself, okay? But there are many more pictures in Eulers. You just open the pages and you see pictures. Now, but the other context that I want to provide is this. And it has to do with, everybody knows, I'm not spoiling the final point that I want to make in here. Everybody knows that Poincaré was the father of chaos. Okay? But he lived in a world that was preceded by Laplace. And Laplace, who probably is also the father of statistics and probability, but the way that he had to phrase these things is, we may regard the present state of the universe as the effect of its past and the cause of its future. That's a beautiful sentence, okay? An intellect which at a certain moment would know all the forces, so this is the idea of perfect determinism, and all positions of all items of what nature is composed, this intellect, if they were vast enough to submit this data to analysis, it would embrace in a single formula the movements of the greatest bodies in the universe and those of the tiniest atom. Never mind that atoms had not been discovered yet, it was a figure of speech, okay? For such an intellect, nothing will be uncertain, and the future, just like the past, will be present before its eyes. So when Laplace came up with the idea of bell curves and all of those things, it was to admit errors in the data, not that the things couldn't be precisely determined. Another one that I want to mention was Poincaré, but this is slightly different. If we knew exactly the laws of nature and the situation of the universe at the initial moment, we could predict exactly the situation of that same universe at a succeeding moment. But even if that were the case, that all the natural laws had no longer any secret for us, we could still only know the initial situation approximately. And this is the key thing, the approximately. It may happen that small differences, small differences in the initial conditions produce very great ones in the final phenomena. They are in a nutshell, you have the idea of Lyapunov exponents and things like that, only verbally. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible, and we have fortuitous phenomena. So now, contrast that with the picture that most of us have that gave rise to Laplace and those 3 volumes of celestial mechanics about determinism, perfect prediction, then kind of toned down by Poincaré, but still not based on any math that he had uncovered, okay? And it's Newton as the all-powerful mathematician. This was how William Blake, who was not a friend of Newton, saw him. But was Newton actually a Newtonian? Did he actually embrace the idea encapsulated there by Laplace that if you know things, you will predict the future? Now, this is not a discovery of mine, it's somewhere in what Newton wrote, and I'll mention a couple of things, but this is what Newton says. Each time a planet revolves, it traces a fresh orbit, as happens also with the motion of the moon. And each orbit is dependent upon the combined motions of all the planets, not to mention their actions upon each other. Unless I'm much mistaken, it would exceed the force of human wit to consider so many causes of motions at the same time and to define the motions by exact laws that would allow for an easy calculation. There also you have the seeds of something like divergence of initial conditions and all of those things. And this is Newton. The other thing that I want to point, and this is Newton himself. So this is proposition 41, theorem 23, 33, 32, and it says a pressure, if you read this, by the way, how many of you have looked through the pages of Principia? There's not a single equation anywhere in the book. It's only geometry. The calculus he reserved to actually be sure that he was proving the thing right. So, proposition, he called this a theorem. A pressure is not propagated through a fluid in rectilinear directions unless where the particles of the fluid lie in a right line. By the way, no one knew that there were particles in a fluid. Atoms had not yet been discovered. And he made this argument, okay, and you can read it. But the most amazing thing about this is that it was a QED. He called this a theorem. Okay? No one now will call this a theorem. So the standards of what people used to call a theorem evolve over time. And on this is something that I want to sort of make some remarks, because Poincaré came on one side, and other people who started put more rigor in mathematics came on the other one. So who was Poincaré? He was called the last of the Universalists, and made fundamental advances in math, physics, astronomy, and philosophy. He was able to write beautifully. He actually produced books that were bestsellers on his time. They were regarded as essential reading for anybody who was cultured in France. And more than that, he was able to analyze himself and make incursions in the psychology of creativity. He was a member of the establishment, okay? His cousin was the Prime Minister and President of France. At one point, he had held the 5 professorships and collected degrees from Oxford, Cambridge, and everywhere. In what was a first, he was president of the Mathematical Society of France, but also of the Académie Française, the literary academy. That was a first. Okay? But more than that, he was a member of a courier of European culture. Okay? The works, as we have said, span 11 volumes. I show the picture of that. He wrote 500 papers on math alone. He was a public intellectual. This is what the book that is still in print today. You can buy it, okay? And I do not know how to benchmark this in 1900, but the first printing of the book within weeks sold about that number of copies, okay? He contributed to a whole range of things, and we will be lucky to be associated with just one in which we made contributions. Algebraic topology, I'll say a little bit more of that. Algebraic geometry, number theory. There are theorems that carry his name, and I will mention a few of them. Some conjectures that he made, they were still unproven until now. He did all of these things. He made some things that had to do with connecting with fluids. People at that time, they were looking a lot of the shape of rotating masses held together by gravitational forces. By the way, you'll think that the paper that has the title on the shape of objects subject to rotation, something like that, you will at least include one figure. There was none. Okay? So he even got into arguments about lecturing. This was the beginning of quantum mechanics. He foreshadowed some things that had to do with relativity. For example, the Lorentz transformations actually are due to Poincaré. You know something that is called Stigler's law. Stigler's law says that Stigler was a fellow here in Chicago, a sociologist. Stigler's law says no discovery is named after the original discoverer, including Stigler's law, because it was proved by a fellow named Robert Merton in Columbia. Okay? But one of the things that is the most fascinating about Poincaré is the three-body problem. There's an entire book written recently by a woman in England, and this had to do with, there's a long, long history here. I'll hit the main points in here. It has to do with the discovery of Neptune, okay? So the issue was that Uranus was not behaving exactly as it should have been behaving according to the predictions of Newtonian mechanics. Nothing of this was in close analytical form. They were long, long expansions. In fact, one of the first tests of Mathematica was to prove some of these expansions. But the point is, Uranus was not doing things as it should have been doing, okay? So a lot of people came up with ways to patch these discrepancies. I think Bessel came with one theory. Some people indicated that the mass of Saturn was wrongly calculated. But the idea that started to take shape was that there was another planet, a trans-Uranian planet, that was responsible for those deviations. And people worked this out, and there were two people who more or less almost simultaneously, John Couch Adams in England and Jean Le Verrier in France, who said, communicated to an observatory, if you point a telescope at such and such an angle, you will see the cause of these deviations. So it happens that Le Verrier was before, he's the one who takes the credit, but John Couch Adams was second, and a new planet appeared. So the faith for people in determinism was unbounded. Nevertheless, there was a problem, and the problem was that people could calculate two bodies exactly, okay? is what gives rise to Kepler's laws, but no one could compute an analytical solution for the three-body problem. So an enterprising fellow of name Mittag Leffler, a very entrepreneurial sort of guy, who you read the biography, it says he married very much upwards. He regarded a journal that he had created, Acta Mathematica, as his personal kingdom. He wanted publicity for this journal, and so he persuaded the king of Sweden to give a big award, a big prize, to people who solve some really open problem. So there were several problems proposed, but the degree of submissions were not that many. One of the problems was the solution of the three-body problem. In the jury, there were people like Weierstrass, for example, and Poincaré submitted the solution, and he was declared the winner. Okay? However, while the paper was being proofed for publication, and eventually the paper was published, one of the young Swedish mathematicians who was helping Mittag Leffler discovered a flaw in the proof. Now, Mittag Leffler had a big political problem because to admit that a solution that would be published was wrong, he had a lot of maneuvering to convince people like Weierstrass. You can read all of this, it's very nice political intrigue. But the point is that Poincaré said, I'll fix this. I'll fix the problem. Well, fixing the problem took, I don't know how many pages, but it was a lot of work. He also had to retrieve every copy that had been sent to everybody and reprint the things. He ended up spending more time than the price that he was getting. Okay? But eventually, most copies were retrieved. Of course, there is one that survives with a wrong proof. And eventually, he fixed it, but he fixed it in a way that it was not satisfying. He won the prize, but many of you may have seen this. At some point in the paper says, when one tries to depict the figure formed by these two curves, these are the stable and unstable manifolds of periodic points, and there are infinite number of intersections, each of which corresponds to a doubly asymptotic solution, these intersections form a kind of net, web, or infinitely tight mesh. One is struck by the complexity of this figure, and I'm not even attempting to draw. Now, this is the root for this. However, was this something that, obviously, he could do all of this with pencil and paper. He couldn't calculate anything using computers as we have now. But I cannot resist a near miss in this. And the near miss is with this fellow, Osborne Reynolds. So it happens that these two guys died within 6 months of each other. The obituaries of both are in the same volume of Nature. And at some point, Reynolds was not as high in the prestige scale as Poincaré was. He was invited to give a talk at the Royal Institution. And the talk was published there in the Memoirs of the Royal Institution of England. It was published in the magazine of Manchester, where he was a professor of engineering. And it was also published in Nature. And this is a paper that is mostly the script of what he said. But in this paper, which you don't see that many papers starting with, in his charming story, The Purloined Letter, Edgar Allan Poe tells how the efforts, he's trying to say that they were trying to find the letter, and the letter was actually on top of a desk. And no one could find it because it was so obviously placed. So the point in here that Poincaré was trying to make is a point of actually mixing, is the study of fluid motion by means of color bands. And in here, I'll mention two things. One is that he says that unraveling the internal motion of fluids, the complexity of fluid mechanics, he kind of throws a jab at the other people who are interested in Neptune, because in respect of the mental effort involved or the scientific importance of the results, referring to work dealing with motions of fluids, this goes beyond that which resulted in the discovery of Neptune. So that's one thing that gets close to Poincaré, because that's how Poincaré started. But the other one is the idea that mixing, and if I had known this when I started doing my PhD and everything, I would have saved 15 years, okay? Reynolds mentioned that mixing was stretching and folding. The stretching, he called it attenuation. But it's very clearly here, okay? So the main reason that I'm mentioning this is two reasons. One is a kind of detour. Why this idea never, ever, ever flourished is because Reynolds himself killed the idea, because he had another idea about the motion of highly disorganized fluid motions, and basically the Reynolds decomposition is there, and one was completely statistical, the other was completely geometrical and deterministic. So this idea killed the other one. So no one really followed up on the previous one. But the other one is that if you had realized that by doing a fluid experiment, by putting a drop of ink in a fluid container, this would allow you to visualize these manifolds and stretching and folding. If these two guys, if he had actually been able to imagine a way of doing the experiment, and this fellow had been able to see it, the history of mathematics and science would have been altered in a radical way. But the point is that no one saw it, and in fact, the discovery of these homoclinic and heteroclinic intersections was regarded as a semi-failure by Poincaré, because when you read the obituary, they mention many, many, many things as really great things that he had done, but the ThreeBody problem starts with a phrase that he did not succeed in solving it, either in the old or modern sense, okay? It's no criticism of his achievement. It is sufficient to say that he opened the way to explore a new region by routes which may ultimately lead to the final goal. Still, people thought it could be done. So it was an idea not taking root, two things that they were close to being connected didn't connect. So I think that that's an interesting thing. But this failure is actually the reason that Poincaré is considered the father of chaos. But the connection in between mathematics and fluid, that was being worked out, but not in this specific case. No one saw this except him. No one really brought this as a serious activity here. And finally, these two never connected. Now, there's another reason that Poincaré's life is worth exploring, and it has to do with this. So, I mean, these people overlap, but these two pictures will be, if we were putting them in a brochure, they will be perfectly acceptable today. Not that one. This is clearly a different generation. But is the role that Poincaré played in affecting art. Okay? And this is an area that has been thoroughly researched, and this fellow, Gerald Holton, who is in Harvard, has written extensively about this. So I'll mention a couple of things, but one of the reasons that I wanted to give this talk, and especially it happens today, is because of this. So this is the drawing room of Niels Bohr. He was no starving physicist, Niels Bohr, okay? But Tuesday next week, I'm giving a talk. They are organizing a symposium about creativity in science and art, because it's the 100th anniversary of the atomic model of Niels Bohr. And Niels Bohr, by the way, you cannot find any of this in Wikipedia, but there is someone who is the director of the Niels Bohr archives who was all too glad to answer inquiries from someone because Niels Bohr had this painting there and is here by this fellow, Jan Metzinger. And Metzinger was the co-author with this other fellow of a fundamental book on cubism. Okay? So the story with Bohr is that complementarity and ideas like that, I wouldn't say that they were inspired by these multiple viewpoints in a painting, but there are books written about this by people who are friends of Niels Bohr's sons. One of them is still alive. I will get to meet him. And he loved to show this painting to people and explain the concept that he saw behind. So in the case of Bohr, it was cubism affecting him in some way, although not much is written about this. But what is much more written about is that the books of Poincaré, they were versions written that were much more people-friendly by some amateur mathematicians. And some of those books, the idea of visualizing things in multiple dimensions, contain figures such as these. And the author of one of these books were those guys, Jouffret and Princet. And these people were the ones organizing study groups, okay, presenting the ideas of the day. And both Picasso and Duchamp came to those. Duchamp much later than Picasso. So the ideas of Poincaré about multiple coexisting dimensions and all of those kinds of things, they inspired in a way, and there's much written about this, the course of art via cubism. But the other thing was the way that Poincaré wrote and the way that he sort of expressed his mode of thinking. The mode of thinking that he put in writing, saying how the ideas occurred to him, was very close to what and it's very hard to say what came first and second, to the way that the surrealists were thinking about art. Almost an unconscious process of putting the ideas on paper, okay? So this is a straight quote from Gerald Holton in this paper in Daedalus. Now, the idea of the thinking in mathematics at a very high level being close to art, and in one case you can say that a painting is created, and without that author of the painting wouldn't exist. And mathematics is slightly different, and I guess you can divide mathematicians in two classes: the ones that think that math is discovered, and the ones that math is invented. And I have some quotes in here, many of which will be known to you, but you cannot really go and study how these people express the ideas about what they felt about math without encountering the word beauty very often. So G.H. Hardy is the one that beauty is the first test. There is no permanent place in the world of mathematics or in the world for ugly mathematics. Okay, that was one that is probably known to many of you. The Hermann Weyl here, it is a fact that beautiful general concepts do not drop out of the sky. The truth is that, to begin with, so this is very, very poetic, and it's about finding the magic key that somehow opens the door from both sides. So I'm not going to read the whole thing, but it's a beautiful quote. I like this one. This is much more down to earth. Enrico Bombilla, he was in the Institute for Advanced Study. He says, my attitude towards mathematics is that most of it is lying there, sometimes in hidden places, like gems encased in a rock. You don't see them on the surface, but you sense that they must be there, and you try to imagine where are they hidden. suddenly they gleam brightly in your face, and you don't know how you stumble upon them. Maybe always we're in plain view, and we are all blind from time to time. So I'm mentioning this because of the connection with, connecting with art and math, because Poincaré was central to this connection. And this is, in the flesh, Mittag Leffler, the fellow who orchestrated the prize, the editor of Acta Mathematica, and he also had this quote, which, if you are in math, I think you should kind of put in your office, because it's such a nice statement about the beauty of the subject. Now, Poincaré himself came and said this: the scientist does not study nature because it's useful, study it because it delights in it. And then he follows, if nature were not worth knowing, life would not be worth living. Okay, that's kind of putting the things more strongly. And all of these things sort of appear in various places. They are very much researched. Jack Hadamard, who was one of, if you stretch things a lot, he was probably one of 3 students that Poincaré had. He didn't have more than 3. And Hadamard wrote about how ideas, how mathematicians thought. This is a very good little book to read. Who were visual, who was not visual in mathematics. For example, Weierstrass, he will put it as the prototypical non-visual, Riemann as the prototypical visual, except that, like most of us, when we write a paper, we don't present the whole scaffold. You remove it, and after you remove the scaffold, things look almost magical. Wittgenstein said, kicking the ladder, okay? Or Helmholtz described the royal path, especially if asking someone inviting you for a lecture and asking you, how is that you did this? You describe this royal trajectory, but actually it was a shaky ladder that got you there, okay? So Hadamard, which you see here, is the one who sort of tried to get into this, how is that people think in this area, and he sort of described people coming on both sides, the inspired by visual things and the ones non-visual, or at least in the final process. So we know a lot about Poincaré because he allowed to be interviewed and subject to tests. People say that he jumped from area to area, that he was completely uninterested in correcting proofs, but the manuscripts that he wrote by hand, they had hardly a line cross, okay? Work quickly. He was always of the opinion that unconscious, and he wrote about how ideas occur to him, and there is a famous scene about coming from a trip and climbing a bus, an idea sort of appearing to him fully formed. On the other hand, he was amazingly methodical. He worked from 10 to 12 and 5 to 7. Obviously, his brain was always connected because no one can have this skill and produce what he produced. But he was very, very methodical, okay? And this fellow, Toulouse, interviewed him and published his findings. And this was the encapsulation, that his Poincaré thought was spontaneous, little conscious, more like dreaming than rational. And this is what, as I said, appealed to the artists of the time. Now, let me make a brief detour in here, because Poincaré was remarkably creative. I mean, he contributed to so many fields, okay? So the best encapsulation in my mind that I have seen of what constitutes creative thinking comes from this fellow, who himself was no lightweight. He was in Carnegie Mellon, contributed to many, many fields, artificial intelligence. He won the computer science. but he won the Nobel Prize of Economics. And what he said was that there were three things that they were the fingerprints of creative individuals, okay? Number one, and this is what may have played the role of Poincaré, except from 10 to 12 and 5 to 7, is continual preoccupation with problems over extended periods of time. It's like you have it in the background of your brain. The other one, and this is a failed test in many instances when you bring a creative idea, is willingness to accept vaguely defined problem statements and gradually structuring them in the course of time. I mean, many times you may have presented an idea that you say, look, this is an idea that I have, and I think it goes like this, and people in the audience ask you for more definition. Well, if you had been able to define it more fully, you have been way out there, halfway to solve it. The idea is that an idea never appears fully formed. They have to evolve. And the other one is the is the 10,000-hour rule, maybe, is extensive background knowledge in relevant and potential relevant areas. You never know what the relevant area is in a field until it's kind of in the rear-view mirror. I mean, for example, no one knew in 1985 that computer science was essential in biology because no one thought that somehow you sequence DNA and decompose it in something that was basically information. So if you had that background area in biology before people had it themselves, you were in the driver's seat. So those were the three characteristics. But clearly, 1 and 2 were completely present in Poincaré's life. Number 3, his first degree was in mining engineering. He even studied reports of explosions in mines. He kind of stumbled more into mathematics. And in physics, he got into physics because he was offered a chair and he had to lecture in physics, not because he formally was trained in physics. So, but the other thing, and I mentioned this in passing, is that the complete absence of geometrical thinking in Poincaré. Not thinking expressed by means of figures. So as I said, you look at this paper about the stability and an equilibrium of figures or rotating masses, the paper is more, I don't know how many pages, maybe 15 pages, but there's not a single figure anywhere, okay? And in fact, if you scan the works, you don't see that many, except on things that I will not mention here. He was part of an expedition because it was very hard to synchronize watches, but this is what gave the idea of the Lorentz transformations. So he went to Ecuador, for example, and in order to determine where you have been and explain, you had to draw the maps of cities and this triangulation and this and that. So those papers, which are very, very sort of, a civil engineer will do that, they were, had figures, but those were not typical of Poincaré. I'm sure someone else drew those figures. But these ones do not. But if you look at things that he has done, for example, the name that we attach to this fixed point theorem is Brouwer, and that's like 1930. Poincaré kind of anticipated this, okay? Is the idea that in a mapping of the domain onto itself, at least there is one fixed point somewhere. And the way that you explain this is with, I don't know, coffee cup and this and that. Poincaré recurrence, if phase space is conserved and you draw a little ball around the point and you move it, at some point, the volume has to intersect where it was. At least that's the way that many of us explain it. All the things that have to do with qualitative theory differential equations, which is foreshadow, I find no way of explaining this unless by drawing a figure somewhere. And this Poincaré-Birkhoff theorem, so this was one in which he published in an Italian journal. He basically said, this is the way it is, but there was no proof. But it didn't take long for Birkhoff, who was in Harvard, to prove it a year after, okay? But the idea is that if you have a perturbation on this figure, which there are some rational orbits and irrational, and some points will have to move out, some have to move in, there has to be some kind of conservation of area, so there has to be, by definition, some kind of fixed points in there. And if you start looking at the motion around those points, you'll discover half are elliptic and half are hyperbolic. So that's the way that all of these things have a geometrical implication. But in the entrance to the Polytechnic, Poincaré scored 0 in drawing. He could not draw. Okay? Now, he could think about figures, obviously, but he couldn't draw. Obviously, he must have been off a scale on the other things, otherwise he wouldn't have gotten into the Polytechnic. Now, I mentioned the Poincaré-Birkhoff. It took 1 year for someone to figure out. Another one lasted like 100 years, and is the one that this fellow, Grigori Perelman, proved, the Poincaré conjecture. This is the fellow who got the Fields Medal and didn't show up for the prize, who won the Clay Institute Prize, I think it's $1 million, and did not show up. He showed up to one thing early on in his career. He now abandoned all math and is living with his mother, I'm told. But this Poincaré conjecture, I mean, even if the only thing that you do in your life is to conjecture something that people cannot prove or disprove, either way, for 100 years, I think you have the future assured. But the other thing is that we know, because he consented to be tested, he was ambidextrous, but had difficulty recognizing left from right. Okay? And as I said, he could not draw, he scored 0 at the examination in the Cole Polytechnic. I think if you draw something, you'll get some points in there. The other thing is he had almost no confidence. As I said, there are probably 3 people who come close to being Cole student. At the same time, the Germans, and I'm going to mention this in a second, Hilbert, the Germans had invented the machinery of PhDs. Hilbert had a lot. The French had none. Okay? So one of the students was this fellow Louis Bachelier, who is now regarded as the father of financial mathematics. And if Ed Olmsted is in here, you will know much more about this than I do. But he was a loner. Sorry, going far. Now, other activities. He got into big battles with Maxwell about explaining things, formalizing. I mean, Maxwell didn't come up with what is now Maxwell equations in the form that they are written now. So lots of people weigh in on how this should be shaped, including Poincaré. But he had very big battles with Tate, Peter Tate, the one of Kelvin and Tate. He lectured widely, okay, from math to quanta. And as I said, he came to the US, he lectured here, and he was also involved in the Dreyfus affair. Many of you, captain from the French army, a Jew, convicted on very faulty evidence. Poincaré was called as an expert witness to analyze the handwriting, and he said, "This is a crappy job. This couldn't possibly have happened." But he didn't publicly declare that the innocence of Dreyfus. But he was deeply interested in contemporary technology, especially the synchronization of time. Okay? He was on the wrong side of a few things, but so was Lord Kelvin. Okay? But for example, these N rays, that they were demystified actually by an American who visited France. He was nominated 5 times for the Nobel Prize in Physics, and eventually he died. Not as many times. In one of the little reliefs that they are at the entrance of Tech, which they are worth studying. There is one that contains the name of Bohr and Langmuir, and another fellow whose name I don't remember. They all won the Nobel Prize in Physics or Chemistry. And then there is Lewis, who, Lewis acids, I do not know if in chemistry, Lewis was nominated, this must be a record, 35 times for the Nobel Prize. Never got it. Okay? But on the other hand, I like the Freeman-Dyson observation. It's better to be asked why did not get the prize, because they have asked him, rather than being asked why you got it. Now, he had a battle with Bertrand Russell. When Poincaré got into the fundamental foundations of mathematics, and that was Bertrand Russell's territory, he said, well, he was already an old man when he became aware of the existence of this subject. And Poincaré was 40. He regarded that as passé. Now, Bertrand Russell lived to 92. With Hilbert, this is the interesting thing. Hilbert was the main proponent for rigor in mathematics, okay? That the QED that Newton did, that was not really a proof. He was an advocate of rigorous proofs. On the other hand, he had tons of figures that for many people weakened the argument, and Hadamard said, diagrams appear in every other page. So he was commenting on his work, okay? But that was the big battle. Now, I mentioned Bertrand Russell. Poincaré died, I'm going to close with this, young. The life expectancy when Poincaré died, but it was highly distributed, was 40. However, it would be good news for this crowd, some mathematicians had amazingly long lives, especially in the context of what they live. I mean, Bertrand Russell, 97, Newton, 85, Jan Brouwer, who I mentioned, 85, Kolmogorov, 84, Weierstrass. I mean, you can go here. Gauss, reasonably young, 78, 76. These people had long, long lives, okay? So, but when he died, in the obituary from Nature, Nature said, remember, Nature is an English publication, okay? The world has lost, by the death of Henri Poincaré, one of the greatest men who have lived in the present century. Okay? His comparatively early death, he died at 56 or 58, in the full vigor of his activity at the early age of 58. Okay? So this was the English commenting on Poincaré. So they wrote 2 articles. One was the obituary, is who came, who said what, where he was buried, that kind of thing. And then they wrote, there were several articles that appeared commenting on his work. Okay? The one that appeared in the US in Science was written by a guy who no one knows now the name, who was at Clark University. And it's a sad story because Clark, at that point, the Department of Math was being closed by the president, and he became so despondent that he committed suicide. According to the accounts, he shot himself twice. I do not know how that can happen, but so that's, yeah. So this is what the English said about his death. But the part that I want to comment more, we know how passionate the French are about the French language. It's regulated, by an academy. There is no such thing in English language. He was an elegant writer. Passion for scientific truth did not suffice for him. He loved literary beauty. He knew that the French language is itself a country, and against every perilous invasion, the soldier of sound speech stood firmly at the frontier. This is a great quote, and coming from the English, that's an absolute delight. So this is all that I have. I'm glad that I had a chance to do this for you, and I'm delighted that you all came to this. Thank you so much.